from Nottingham. And he will be here tomorrow for the piece of Cork. And he was kind enough to tell us about this quantum Markovianity in fundamental thermodynamic resource paper that has been published last year. And he's so he got the PhD in 2007. And the position in Nottingham is also was very soon in 2011, was it?
2009.
2009.
Yes, January.
And
hello.
He's a good professor there. He's been research director. He has been interested in this, well known for his contribution in quantum information and many related topics also from quantum evolution, thermodynamics, and so on. And he was awarded a grant of the ERC, the starting grant, in 2000.
I think 15, something like this.
2015,
Yeah.
2020.
Yeah.
Starting grant ERC. And we are very happy to have him here.
Thank you so much for this. It was nice that we could organize the seminar at the last minute, and thanks everybody for being here. Yeah, so this is a nice work that I want to present today because I think it fits with the interests of many people in this group, and I'm happy to have more discussions afterwards. And I mean, my name is there just because I was hosting Guilherme, but most of the work was done by Guilherme Zambon, who is indeed, I think he's finishing his PhD in São Carlos, USP with Diogo Soares Pinto, but he got funding from FAPESP to come for 1 year in Nottingham, and we were working on this stuff. So the idea is that we want to, of course, it's not the first time this question has been asked. What is the role of non-Markovianity in thermodynamics? And many works, including from this group, have already provided answers to this in interesting contexts, which range from fundamental to more open systems to more operational. We were trying to find some sorts of more maybe mathematically oriented, standardized framework in which we could really characterize the advantages that can arise in thermodynamics from having processes which have memory, which are non-Markovian. So how does this thing work? Let me see. This is good. Yeah. So quantum thermodynamics is a field which I don't know if it's new anymore, right? There was a conference already organized by Roberto, and I think that was probably the third quantum thermodynamic conference. I think this was 10 years ago, no, or 2015 or something, yeah? 15, 16, yeah, so it was 10 years ago. So the field has been evolving quite rapidly, and people are converging towards this field from different communities. So, of course, it sounds like an oxymoron, right? Because thermodynamics is something that implies large, quantum seems to imply small. But on the other hand, the question is, how are the laws of thermodynamics, which have survived so many revolutions in physics, still going to apply at the level of individual quantum systems? And so, of course, this combines interest in dynamics of open quantum systems, but also we can understand thermodynamics from a quantum information perspective in terms of characterizing it as a resource theory, which is something I've been working on. And many of these different aspects converge into the book, which I think is already now old. I think we published this book maybe more than 5 years ago. At the time, it was like the state of the art of the field. It's like 1,000 pages long. There's about 100 authors contributing chapters to this, but there's more and more that has come after that. So for the purpose of this talk, we are interested in the resource theory perspective. So we understand thermodynamics as the resource theory of quantum thermodynamics as the resource theory of quantum states, processes, and so on, out of equilibrium. To formalize this, let's just go take one step back and talk about resource theories in general. Now, this is a little bit of an analogy, if you like. So the idea is that we want to classify, in the simplest instance, states and operations in terms of their usefulness for some task. Now, the task might change, although the underlying mathematical structure might remain general for different tasks. Think about it, maybe we have some old relative that we didn't know about, and at some point we get notified that this relative unfortunately passed away, and we have inherited some stuff from them, and we don't know what to do with it. So my great aunt Birgit left me a basement full of junk, which I don't know what to do with, and I start experimenting with this machinery, and then I realized at some point that If I put some specific inputs to this machinery, maybe I don't get anything useful out of it. But if I put some different inputs, then I get some useful effect, like, I don't know, lighting up a light bulb. This metaphor just says that we can then classify things which are given for free or that we are allowed to implement given some physical constraints as operations that we call free operations. While the operations that are not free, they might need the use of some resource in order to be implemented. And on the other hand, the inputs in the classic formulation of resource theories, they can be states, and we can again have states which, if they can be created just by use of free operations, then they do not carry any resources. They're free states. If we use free states and manipulate them with free operations, we cannot create any resource, and we cannot increase the amount of resource if we send states which contain some resource through free operations. So there's lots of constraints which come out of this. And the most famous example of resource theory, which has been studied since maybe 3 decades in quantum information, is definitely the use of entanglement. So in this paradigm here, we classify states which are entangled as useful for many things. I don't know, cryptography, teleportation, some versions of computing, and so on. States which are separable, they would be free, not containing the resource we care about. And the operations that are free are the ones that describe the paradigm in quantum information of distant observers, which operate each of them locally on their system, and they can communicate classically. So local operations and classical communications are free. By using those, you can never create entangled states out of separable states, and you cannot increase the amount of entanglement in states. But this kind of structure can also apply to different concepts. So for instance, we have studied a lot resource theory of even simpler objects like superposition, coherence, imaginarity, magic for quantum computing, and many other things. For thermodynamics, if we want to understand the structure of a theory in this respect, then we have to think how to code the fundamental laws of thermodynamics into constraints which somehow make it clear what is the resource and what we can and what we cannot do. So the laws of thermodynamics, we can present them in many different ways, but let's just stay informal to begin with. And I used to think of them as 4. So there's the law, the 0th law, which just says if A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. So thermal equilibrium is a transitive property, and this thing defines the concept of temperature. Okay. Then first law is conservation of energy. Second law, you can think of so many different ways, but this one is the one that imposes the most stringent constraints on what is possible, what is not possible. And then the third law, once you have formulated thermodynamics as a resource theory, actually the third law, you do not need to impose it as an axiom. It can be derived, it can be proven that if you, in the sense that if you want to cool some system towards the absolute zero, this would need you to expend an arbitrarily large amount of resources. So that makes it impossible, in a sense. So thinking of these laws in mind, let's try and figure out what can we do with thermodynamics. So what we have, we start with a system with its own Hamiltonian, prepared in some initial quantum state. And then we also have the environment. So what we assume here is that if you just leave some system thermal equilibrium with an environment, it will thermalize. Okay, and we can draw as many thermal states as we like from this environment, and these are given for free. So having the 0th law in mind, thermal equilibrium states are the ones that we consider to be free. Right, so we have this reservoir at some given temperature. It has its own Hamiltonian. What are the operations that we can freely implement? Okay, which are the ones that are not supposed to give us any useful effect. These are operations that should comply with the first law, so conservation of energy. So the idea is that we can act with unitaries that operate on system and environment, and they should conserve the total energy. Okay, so they should commute with the overall Hamiltonian of system and environment. So free states for us are thermal equilibrium states for the respective object with the Hamiltonian. Free operations on the level of the system only are those which are obtained by possibly having unitary energy preserving operations on system and environment, and then tracing over the environment. This defines a map, a quantum channel at the level of the system only. which we denote like this. And these kind of channels are called thermal operations. Okay, trace over the reservoir of the unitary applied to system and reservoir, where the unitary is energy preserving. So we will, in the initial formulation, we will say thermal equilibrium states are free, thermal operations are free channels, and then we see what to do with it. And people have developed this resource theory, but we haven't really explained yet what is it for, right? So what does it mean resource, and why states which are thermal equilibrium are free, while states which are away from thermal equilibrium are useful for something? And so we need to define some task here. And the task that typically we care about in thermodynamics is extracting work. Okay, to move some piston, to power a train, to power a power plant, to run some refrigerator cycle, and so on. So in order to define the task of extracting work, we need to bring in an extra piece of the puzzle, which is a battery that we want to charge, in which we will store the work that we can extract from our system. So we have the system, and in the back of our mind, there's the reservoir that provides supplies of thermal states. But then we have an additional system that we call a battery, and this is, you can think of it as a qubit. Okay, it's a qubit with a Hamiltonian which has an energy gap, E, and then, so there's 0 at the ground state, and then the gap E, this is the excited state. If this qubit is in the ground state, you say it's not charged. If it is in the excited state, then you have extracted an amount E of energy. Okay, so the goal is that we start from our system and an empty battery, do some allowed transformation, and see how much we can charge this, how much work we can extract from the system, okay? By means of thermal operations. Now, of course, if we just do it on a single shot, it's not going to be very efficient. And there's a lot of interest in doing thermodynamics with single shot, and this leads to a different resource, which people quantify through the concept of ergotropy. But when this resource theory was developed back in the day, we were looking a lot more from the quantum information perspective, and the idea is that we can operate on many, many copies of our systems and look at the rate at which we can extract work asymptotically in the limit of infinitely many copies. So let's try and write formulas and make sense of them. We start from n copies of our system in a certain state, and then a certain number of copies of empty battery. And the goal is to look at the best we can do only by using thermal operations, so that we transform the overall system and battery component in whatever it is for the system, we don't care, but all those batteries need to be charged. Then, of course, it's not always possible to charge as many as the initial copies of the system. So this rate is what characterizes how much work we can extract from the initial setup in the asymptotic limit. So we can define the extractable work from this state as the maximum of the rate R of fully charged batteries that we can obtain by operating on n copies of our system by means of thermal operations. Now, this is an interesting quantity, and what it turns out is that this quantity can be computed. So if we really take the limit, the asymptotic limit, this maximization can be computed, and it becomes equal to a geometric characterization of the state of the system only. So this extractable work will converge, apart from the usual Boltzmann factor, to the difference in free energy between the initial and the final state, which is nothing else than the so-called relative entropy of athermality. Now, this gamma is the thermal equilibrium state of the system, and this quantity here is telling me how far in the relative entropy the initial state of the system is from being a thermal equilibrium state. So in the asymptotic regime, if I start with the thermal equilibrium state, then it means by means of thermal operations, I cannot extract any work from this, even in the limit of infinitely many copies, which justifies the fact that we say those states are free. They do not produce any useful effect. The further my state is from thermal equilibrium, the more useful it is as a resource for work extraction by means of thermal operations in this specific definition. So that's interesting, and I think this is going to be our basis. So whenever I talk about work, I'm not referring to ergotropy, but I'm referring to this asymptotic setting for which work is just becomes equivalent to difference from thermal equilibrium. And interestingly enough, then one can also consider the reverse problem, like we do in entanglement theory, for instance, of spending some work to create certain copies of our state. So we start from fully charged batteries, we deplete them, and we prepare states that we care about. That's the concept of work cost. And what people have shown is that the resource theory of thermodynamics with thermal operations like this is actually asymptotically reversible. So it costs as much work to create certain copies of my state asymptotically from a bunch of charged batteries as the work that we can extract back from the system. So this is not always the case for resource theories. For those who are interested, not all of them are asymptotically reversible, and this has been contentious topic for the past few years, even in entanglement theory. That's nice. This is work extractable from states. Of course, that's not the end of the story, but already this gives us some interesting point of view for which we can try and look at the interplay between other resources and how they can help or hinder the process of extracting work in quantum thermodynamics. So we have established that being far from equilibrium is the main element that we care about. And so we can look at how other aspects of our systems can basically input more or less athermality so that we can extract more work from our systems. And this is something we've been studying with members of my group for the past few years in a way or another. I'm not really into thermodynamics, but I keep getting people who like it, so we do interesting work. So in these two works, both of them, I think there was Benjamin Morris involved, who is now a police detective, very successfully. He had very good ideas and is now applying them to the real world to catch criminals. But he spotted some nice features of nature back in the day when he was a PhD student in our group. So here we were looking at, for instance, the idea in which maybe you have some constraints on analysis side and you want just to help Bob extract as much work as possible on their side. So we can look at the role of correlations in a bipartite scenario and communication in order to enhance the work extraction. We found here that both classical and quantum correlation can somehow enhance the amount of work extractable by Bob under different constraints, again, in the same setting. This work was also quite interesting. We were looking at another very unlikely resource, which is ignorance. So we can have situations in which maybe I don't remember if I talked about this in some conference, maybe the time where you were, I don't remember. I think I talked about this work when you were in Nottingham for that workshop, Paolo. So yeah, so you can have the Gibbs paradox. It's about having two species of gas in a chamber which become eventually not distinguishable, and whether the entropy, the work that you can extract from them, how it depends on the distinguishability between these two species. And what we found here is that classically, if you do not see the degrees of freedom that distinguishes these two species, then effectively, even if you remove the separation in the middle, things just mix up and nothing is happening there. But in the quantum case, even for observers that are ignorant to the difference between these two, there's a way in which you can still extract as much work as if you were fully aware of the statistics of the particles. And this, we found it surprising. So we thought it was a quantum reinterpretation of the Gibbs paradox that shows that ignorance can also play a role in enhancing work extraction in the quantum regime. But of course, in this talk, we're going to look at the role of non-Markovianity. And to get to non-Markovianity, then we need to elevate the resource theory 2 floors up. So we have done it from states. Now we have to look at work extraction from channels, and then work extraction from processes, which is even more than channels. So the first step has been done, work extraction from channels. And I'm going to give intuitions about everything. So there's lots of formulas and proofs in these papers, but I probably not even read them myself. So what I understand from them is as follows. So what is a channel? You have just, you prepare your system in a certain state, then it goes to a completely positive trace preserving map, and you get the output at the end. And we want to say the concept, again, asymptotically by means of thermal operations, how much work we can extract from this channel. Okay, the idea is quite intuitive, and it turns out to be the best that you can do. The idea is we are looking at the net difference between, I will spend some work up front to create an input here, and then I will look at the work I can extract back from the output of the channel. and just look at the difference between this. And then I have to maximize the difference over all possible input states, basically. Okay, so the extractable work from a channel is the maximum difference between extractable work from the output minus the work cost of creating the input. So it can also be that maybe you just send in a thermal state. So you don't spend anything here, and the channel, if it's non-thermal, it will give you some extra work and you gain it back, but that's not necessarily the best, okay? It could be that it's better to invest more money and then you get a better reward at the end. So people have shown that this quantity is again reversible. So how much work you can spend to create, to implement a channel is the same as how much work you can extract from the channel that corresponds to this maximization. That's already a little bit more difficult than doing it from states because there's maximization involved. States was just calculate relative entropy from the thermal state. Here you need to do an optimization. Nice. And as I said, we want to go now into dynamical processes. So I'm not an expert in this, but let's just try and give the idea again. So people like Giulio Chiribella and his group, they have formalized the concept of process tensors and quantum comps very extensively, and this is now being used in a lot of contexts. What is the idea behind it? So we want to describe a dynamics, an open system dynamics. And many people, probably you more than me, we usually do it with continuous time. So master equations, dynamical evolution, that's fine. But again, coming from a more informational computational point of view, then we can discretize the time and think about sequences of operations that are taking place and interactions that are taking place on our system. So we have a system that we can control. So the idea is that at given times, we can implement some maps as a control for our system. These are the sequences A1, A2, and so on. In between, our system is evolving beyond our control due to interaction with some environment. And this evolution we describe with this object that looks a little bit like a comb. That's why mathematically you have that these process tensors have a structure of a quantum comb, which means that, okay, you imagine there's some environmental degrees of freedom here, and there's going to be some interaction with these environmental degrees of freedom, but the channel moving forward means that the information here is carried forward as a memory and can influence the future steps. Okay, so what interaction happens here is influenced by the past of what has happened before in general. So the gray part is our control pulses, and then the green part is a process tensor describing this uncontrollable evolution. At this stage in this graph, the output state is going to be a concatenation between this dynamical comp and then my individual sequences. Of course, I can get clever as well. So if the environment exploits temporal correlations, then I can also do that. So I can even try to counteract the action of the green process by exploiting ancillas and memories, which would probably help me prepare more efficient states or realize more efficient tasks. So we can replace this simple sequence by another comb here. And so we can describe a general discrete multi-time dynamics as if you read these papers, this object is usually called the link product, but in general, it's a concatenation between this comb, that is dynamics, and then the comb on which I have control, which is this S. And notice I don't even have the initial state anymore, because you can imagine it's embedded into a possible preparation here. I don't even have to create a state. It could be that it just starts as a process of interaction with some ancillas, but the final state is defined this way. So there's lots of mathematics involved, if you like. You can always characterize these things. So these are now, you can imagine these are transformations which map channels into channels. No? So if I have a channel like before, for instance, this one, I can embed it into this and it becomes a different channel. Okay, so these are sometimes called supermaps or super channels, but we will just characterize them visually in terms of these combs. Nice. And so what I wanted to say about them, yeah. So you can always, like you do with channels, that we can bring them back into a duality with states. We can use Choi isomorphism and then characterize channels by means of the associated states. there's also the concept of choice states for these processes. So many things have been defined by just remapping these process tensors and then effectively projecting them into states by means of choice isomorphism. But in general, let's just keep the visual running. We can characterize two different kinds of processes of this sort. So what I said is that in general, they have sorry. Huh? I don't know. There's something here. Maybe a time. Okay. They have these links at the top, which means that there's memory involved between the different steps. So if we just want to represent them as sequences of channels, that's fine, but they have to be channels with memory. So in general, I can always decompose a comp like this into a sequences of channels, but the channels beyond the first one will depend on what was the input to the previous, on the whole history. Okay, so I have this one is a definite channel, and then which this is, it depends on what I have sent through here. Okay, so we can resolve the links, but we have to keep the dependence on the past history. That's the general structure of a comp. When this is not the case, when the future channels are defined independently of the input to the previous ones, then we say that the process itself describes a Markovian evolution. Now, lots of people have been looking at quantum definitions of Markovianity, and typically it's done in terms of divisibility under complete positivity, CP divisibility. I like the fact of looking at this definition from the process tensor point of view, because actually this shows that definitions are not exactly equivalent. So there's been a lot of debate about whether CP divisibility is or is not the right analog to classical Markovianity. And it might not, I mean, maybe for continuous time, this question is still open, but for processes made of multi-time discrete sequences, I think it's quite unambiguous that if your comp is described as a sequence of channels without memory, then you call this process Markovian. And when that's the case, then this implies CP divisibility, but there's been examples shown in the papers by Kavan, Modian, and so on, of the other way around not actually being true. So there can be channels which are CP divisible, but they're still not Markovian in the sense of this. So they keep some kind of hidden memory that couldn't be seen in the CP divisibility. So we will take as definition of Markovianity for processes the one at the level of the process tensor. Now, fun fact, when Kavan and so on, they were developing these works, they were formalizing non-Markovianity for process tensors as a resource theory on their own right. Okay, so you have athermality for thermodynamics, then you have non-Markovianity as a resource theory. So you can also characterize which transformations of processes, which are super maps, do not increase non-Markovianity and so on. So they came up with criteria, and then they came up with potential monotones. So measure that should be a valid measure of non-Markovianity. And they claimed that, of course, their measures satisfy their criteria. It turned out it was not the case. So they had made a mistake there, which is funny, because then when Guilherme came in Nottingham, we were working on this paper. At some point, he realized the mistake, and they fixed it, and he ended up publishing a paper on his own before we had this one, which is FISREV A editor suggestion, very good paper, in which he proposes valid measures of non-Markovianity, which actually satisfy the resource theory criteria that were proposed in the previous papers. And we can adopt one of them, because eventually we want to make a comparison between work extractable and amount of non-Markovianity to see really if there is a quantitative resource role of one for the other. And so what do we do? So let's try to make sense of this definition. It's again a geometric definition. It's again about, we want to quantify how non-Markovian a process is by looking different from being Markovian it is. But this difference is a little bit subtler, because what we have to do, we are interested in looking at the characterization of the green comb here, okay? So how non-Markovian is this green comb? And we do this by comparing the relative entropy, where we have one input being the output of the given process, concatenated with the control process S, and compare this with any possible Markovian, in the sense of the previous definition, comb, so the one which is just a sequence of blue channels here, concatenated with the same control. So this is the relative entropy. We compare how different the outputs are between our process and any Markovian process, maximize this over the choice of the control, and then minimize this over all possible non-Markovian channel. It's even worse than before. It's a min-max. So I don't think we have been able to calculate this. So if you give me a random process, even numerically, this is not easy. But we have some very special examples in which we can either bound or evaluate this if the process is simple enough. So we have them in the paper. But that's a definition that, at least formally speaking, satisfies the good criteria. We can adopt it as a valid measure of non-Markovianity, and it will enter in our characterization. So now we have the two resource theories, and the question is, what's the interplay between them, which is what we want to answer. What's going on here? Come on. Fine, I'll do this one in this paper. So the answer probably already know. Of course, we want to get it affirmative. So let's try and derive it. To answer this question, what we need to do is do the next step, as I said. So we need to define the work extractable from a generic multi-time process. We know work extractable from states and from channels. What about from processes? And here is where the things become interesting, because we couldn't find one answer. So we actually found that at least 4 possible ways, incrementally stronger, of protocols for which we can extract work from multi-time quantum processes. And in characterizing how they compare with each other, we understand the role of non-Markovianity as a power-up for this protocol. So our hierarchy, the names are from Guilherme, so identifies 4 different ways of extracting work, which I will explain one by one. One is called sequential, then joint, then global, and then comb optimization. I don't think that's the end of the story. There can be more, but for these 4, they were already sufficient to finalize our conclusion. And the question is, this is not working for me anymore, but it's okay. I think I messed up. Oh, no. I messed up just back and forth. This one is fine, but this is okay. So the anticipation is the sequential protocol is the best that we can do if the process is Markovian. So if the process is Markovian, all the others, they just collapse onto the sequential one. But if the process is non-Markovian, then by exploiting suitable features of non-Markovianity, we can unlock extra work that we can extract from the process. So it's just a matter of being more and more creative in characterizing how we can manipulate this process by trying to extract as much work as we can. So let's see. What is a sequential pro? For all the discussion at this point, I will consider just 2 steps. So a general protocol, a general process, first channel is fixed, second one depends on the input that I send through the first, okay? So it can be non-Markovian in general. How do we define the work extractable from here? First try, we can effectively treat each of these 2 as channels. The second one gets defined once we have operated on the first, so we can go in sequence indeed. So best work extractable from channel P1, what do we need to do? We need to do again this difference. So optimize over this input and look at net work of the output minus work of the input that we have spent. That's it. So once we have done this, we fix this, so this channel becomes defined, and so we now characterize the work extractable from this channel separately, and we do it again. So we optimize the input for the second, and we extract the work, and the total work extractable this way, by operating in sequence, is just the sum of the individual work that you could extract from each of those channels. That's it. Now, if the process is Markovian, of course, there's no dependence like this here, so that's really already the best that you can do, because the channels are independent of each other, and so the total of the work, you just optimize each of them independently. There's nothing to be gained by just trying to collectively input different sequences of states, because they're independent anyway. Okay, so that's the best that we can do. But can we do better if the channel process is independently non-Markovian from the beginning? Yeah. So at this point, we have already cashed in the work here, and then we look at how much work we can prepare there. And so the work from each channel is just independently the difference between the output and the input cost, like we had defined before. So let me go back here. So work extractable from a channel is the difference between the work of the output minus the work cost of the input, optimized over each row. So if we have two channels, the work extractable from the first is the maximum of this difference over the input that is the best for the first only. The work extractable from the second is the maximum difference over some input that is the best for the second only. Okay? Now, this already anticipates the next slightly better strategy, which is when we at least try to jointly optimize the sequences of input states. Okay? So we can still treat each channel for independent work extraction, but instead of optimizing the row 1 here first, which affects the other channel, and then optimizing the second one, we try to look jointly at what is the sequence of input states that we can feed through both channels, so that this will maximize the overall sum of the extractable work from each channel. And it can be that maybe I spend more upfront to create some row 1, which by itself is not optimal only for this, but this one will have an influence on the channel next, and I can find a combination of row 1 and row 2 that gives me more work totally cashed in from both channels. And this is exactly what happens, because one can show that the work defined this way is in general larger than the one from the previous protocol. And the difference of the output of this procedure versus the purely sequential one, we can bound it from above by a function that depends on the amount of non-Markovianity of the process P. Through that complicated measure with the min-max, we cannot compute it, but we can show that the amount of non-Markovianity bounds from above the difference here. So in other words, as I said, if the process itself is Markovian, this thing is 0, and this difference is 0, so you don't gain anything. And if it's slightly non-Markovian, according to that measure, again, you might do a bit better, but not necessarily. If it's strongly non-Markovian, you have at least an upper bound that tells you that in principle you might gain more. Now, this particular bound is not necessarily tight, but at least there's a direct continuity relation between the amount of non-Markovianity and the amount of gain you get by even trivially considering an upfront investment in the choice of the input states. That's why we say this work investment can unlock a little bit more work.
Okay. You have only one, so the P1 and P2 condition by one, but the P itself.
P itself, it means the sequence of every. P itself is the two-step process. So when I talk about P, it means this and this. The overall thing which we have decomposed in this way. It's the whole process. Yeah.
So then, yeah.
So the process is decomposed in, yeah. Yeah, it could be different. The second one will be different, yeah, depending on how to choose the input for the first. Yes. Yeah, you're right. You're right. What else can we do? Then, okay. The difference between this and the previous thing is we can still optimize the whole sequence of inputs, but now it's just a matter of how we cache it back. Okay, so before we were first optimizing the whole inputs, but then we were extracting work from here and then from there. Why do we need to do that? We can just store the outputs of the first channel and then eventually get all the work back from the final output of the process. And that's what we have done. So we are exploiting memory here in keeping the outputs until we just extract work from the end. So the final work in this process is given by the work we extract from the final outputs minus the individual works that we spend to create the inputs, which we have jointly optimized anyway. And this is in general superior to the previous case. And again, every time we have this thing at the bottom, I'm looking at the difference between work extractable in the current step versus just the step before. And this is my favorite step of the hierarchy, because here, first of all, you don't get weird factors, but you really get the amount of non-Markovianity bounced. And it's clearly the temporal correlations in the storing of the outputs which matters here. That's why we call multi-time correlations. So the amount of non-Markovianity bounds the extra work you can do between step 2 and step 3. And this bound, we could prove it's tight. We have examples of cases in which you can actually achieve as much more extra work as the amount of non-Markovianity of the channel. So I was happy. We didn't even know it was tight. Then the referee asked, and then the example we already had, we showed it was actually tight. So we're happy. And then what else? The final one is, why do we even have to bother with all these individual strategies? So, okay, so far we were looking at sequences of inputs and then works, but in the end, we can just consider the most possible general comb here that we have in order to encode all our preparations. So this might encode sequences of inputs and storing the outputs, or it might just encode some more complicated process that involves interactions with ancillas that we don't know nothing about. And in this way, then, of course, the output work is just what we net at the end of the concatenation of these two processes, minus the cost of creating the gray one. That is something that we don't really know about. Yeah, so maximum work of the output minus work of creating the comb. That's an open question. How do you quantify the work cost of combs? Because the whole paper was about extracting work from combs. And now I'm claiming some work cost of the comb. Now, what we do in the paper, if you read it, we postulate a possible work cost of the comb in terms of explicitly presenting a strategy for creating it based on system ancilla interactions and channels for which we know all the individual components. That might not be the most efficient way of creating the comb. So if the work cost of the comb is not that one, it means there must be some more efficient way, which means the cost is even lower. If the cost is even lower, this overall thing goes even further up. Okay, so for this step of the process, we have already gained something compared to all the previous one. We might gain even more if we're able to find an efficient expression for the work cost of combs, because this will net us even more extractable work from the overall process. And again, here we can show this. We used, in this case, correlations with ancillas, which form this comb overall. Then the extra work we get compared to the global one is again upper bounded by a quantifier, the same quantifier of non-Markovianity with this weird power. So I think we can bring this all together now. So what we found is that this is Markov, this is not Markov. So yes, so if the overall process is Markovian, all this hierarchy collapses, and the sequential optimization is the best we can do, and the work extractable is just the one corresponding to extracting work from each channels in the sequence. If the process is not Markovian, you gain extra bits of work at every step of the hierarchy, which are overall jointly bounded by functions that depend on the amount of non-Markovianity in the system. So if this amount of non-Markovianity goes to 0, everything will collapse. If the amount of non-Markovianity is large, we cannot prove that these things are large in general, but we have cases in which really you can net as much more work as the amount of non-Markovianity modulo the constant here. So I think, I don't know whether it's conclusive or not, but I think this is sufficiently convincing that we can have non-Markovianity on one hand as a resource that can enhance extraction of work from dynamical quantum processes in the sense of making them overall more useful, more non-thermal, and more, of relevance for thermodynamics. Now, there was lots of formulas here, but I think my preferred visualization of the hierarchy, there are some examples in the paper as well, which I don't remember now because today I didn't have time to read it again. So there are specific combs in which you show that every step is actually sharp. Okay, these are examples of processes for which maybe this is strictly worse than this, and this is strictly worse than this, and so on. This one in the middle is the one for which we show that that bound is tight, and I think this is very similar example to what they used already to show that non-Markovianity and CP divisibility are not the same thing. But the way I see this, I don't know if you're familiar with Dragon Ball Z. Basically, that's the situation. And of course, now I know there are many more levels, yeah? But if you stick to Dragon Ball Z, sequential optimization is base Goku, then the Super Saiyan 1, 2, and 3. And that's the best that we could reach in this paper. Of course, I'm open to, reaching new heights, God level, and so on. But that's something we need to consider in the future. So I think this answers the initial question in the affirmative. We understand from the point of view of process tensors that non-Markovianity, properly characterized and quantified, is a fundamental resource for thermodynamics. It gives a power up in the extractable work. And we want to do a bit more, but unfortunately I lost Guilherme back to Brazil, so I think I need to find some more people interested in helping me with this. So I want to go, definitely I want to answer the question of the work cost of tensors, because I want to see again if we can show that things are reversible for the best strategy, as it is the case for channels and states. And then I want to go, all of my paper here, they were about sequences with a definite arrow of time. But there's even another resource lurking in the background, which people are interested in, and they use process tensors to characterize, and this is about indefinite causal order. So I want to see whether you can combine maybe indefinite causal order in order to get a definite assessment of its power for thermodynamics. And I think the framework is the same that we have already used. We just need to relax a little bit our assumptions. When we started this work, we didn't really want to go asymptotic because it seems a little bit too information theoretic and less practical. So we wanted to consider the usual setting of what is a cycle, no? Like in our car and in a fridge. So we have a system, and then how much work you can extract just with one closed cycle by means of a unitary operation. That's called ergotropy, and it's different from relative entropy of athermality. So there's some passive states for which you cannot extract any work in one shot, and they're a bit more general than just the thermal equilibrium state. So we wanted to do everything for this, but we couldn't get nice mathematical bounds. I think I'm still interested in looking at the role of non-Markovianity, either in more physical dynamical evolutions, not just some channels that we define by circuits and they don't represent the real world. And on the other hand, by considering more practical versions of work and its use. And experimental collaborations, I learned that you do this successfully. So it would be good if there was a platform around for which we could show even these simple things, maybe even the academic examples that we have found that show the hierarchy of our steps. I think I'm okay with time, so thank you.
The question session, and then I ground to another meeting and someone is going to share. But maybe we can start with very few comments now.
There's official information here, very nice. I don't know who's.
I don't know.
Metrology. Yeah.
Can you use the difference between process, sorry, and the normal channel?
No, channel is a channel. Process is a sequence of channels with memory. So it's the process is a map from channels to channels. The channel map state to state. Yeah.
So, but you can express everything in terms of channels.
You can. You will have sequence of channels with some memory. Yeah. Yes.
But that step, there is no.
No, one step is just one channel.
It's just a channel.
Yeah, one step is just a channel. Yes. Here.
Well, all these papers, so what you mean the work that you can extract in terms of this quantum method, not they have a battery of how much work you can store it.
Yes, but in the asymptotic limits through thermal operation. Yeah, yes, yeah. To the definition of work. Yes, of course. Yeah. I don't think the slide is precise. Probably I omitted some terms there. Yeah. Just to give the idea. No, I think it's this one.
Yeah, that one. So here, when you define the thermal operation,
yes,
then you treat the battery as your environment. No, you have a
that's not. No, the environment was not represented here. The battery is a different system. So.
Okay. So the thermal state is when it has equilibrium with that environment. Yeah. Okay. That's all.
Thanks. Yeah, there are three different Hamiltonians involved: the system, the environment, and the battery system. You're right. Thanks.
Other question, Luisa?
Hi, thank you. So it's my question, I think, is about the definition of non-Markovianity. when you define it, it depends on the initial condition, let's say, right?
So what we're saying is there is a formal definition that you can find in those papers through the choice state of the processes. But the idea is, in general, this one is equivalent to this when there is a dependence on the previous history. When there is no dependence, so when a comb can be decomposed as a sequence of channels where each channel is not dependent on the history of the previous ones, then you say it's Markovian process.
Sorry, no, I meant the measure.
The measure,
thing.
sorry, the quantifier. Yes, yeah.
It depends on S.
Yeah, but you remove the dependence because it's maximized over S.
Yes, so that's
At the end, it only depends on P.
But this is relative to one specific S. In the end, you kind of
You have to try all possible S's and look for the one that maximizes this difference. And then you minimize this over all possible M. So at the end, you see, we minimize over M, maximize over S, everything just depends on P.
Yes. But then when you have the inequality there that you said can be tied, so when it's equal, is it that S that maximize this the same as on the other side of the inequality?
Wait, let me go back to the. Why it's so slow? This the second step, yeah?
Yeah.
So again, this is the N of P itself. I don't remember. That's a very good question. So whether the S that optimizes is the one that just corresponds to preparing this. We have to, let me look at the example so we can comment. It's not always tight. We have found examples for which it is tight, yeah? So in the example is the one that is on this page, this channel here. So I think if I have to go back and read the paper to characterize what is the best sequence of inputs, I think what is happening here, this is a swap gate. The environment is prepared in a maximal entangled state, and then we have another swap gate, and then you just trace over. What was the best input here? I don't remember whether it was a thermal state on one hand and just a plus state on the other. And I will double check. I think I don't remember, honestly. I think in the supplemental material, we must have computed it to show that it was the case. So probably one can find that the best input sequence is indeed the best comp that characterizes it. I don't think here we need anything more than just preparing two inputs, just the same two inputs. So probably yes.
Thank you.
It's some section of supplemental material that we added at the end, where we
More
show the
questions?
calculation. In general, if you just give me some random I think it's bad. That's right. So the previous people, Cavan, Modi, and so on, they had proposed some measures which were computable easily numerically through some semi-definite programming, but then it turned out they were not monotones. So Guillermo's measure is not friendly, but the previous measures by Cavan and then some other measure that Guillermo proposed, they give bounds on this thing and they're actually more easily computable. So the optimization by itself is bad. If we can map it back onto choice states, then it becomes more feasible. But then sometimes you have a projection onto channels which are disallowed. And so this made the measure not suitable. But some bounds, it's okay. Bounds, it's okay. The exact computation, not so much. Maybe for 1 qubit channel is fine.
I was wondering, like, what is the role of the source of the non-Markovianity here? Like, because in the bounds you have like the amount of non-Markovianity, but I think that maybe how tight these bounds are. Like,
yeah, that's a good. So as I said, so let's go back to. So the ones which are from here and here, they give these weird terms. It's proportional to this. It's a lot bigger than that. These two bounds, they come directly from some continuity bound that were in the previous paper by Angela Capel and others. Funnily enough, that paper was also wrong on the published version, but the archive was corrected. So luckily, this didn't affect our paper, but we told them they fix it. And they're not tied from start. It's a continuity bound. So you just show that if you have a state a little bit away from another, somehow some quantity through an expansion changes not that much. So this is definitely not tight. The one in the middle is more related to the non-Markovianity that we know about, just carrying out some memory, and so it gives the different things. So there is room for improvement in these two things up here. I think we wanted at some point to bring these bounds further down. So I think we have to probably start from scratch to derive it, because we have not really taken full advantage of the nature of non-Markovianity, as you suggest. We have only taken it once in the middle here. The other ones, we just were lazy enough just drawing results. But we know they're not tight. So this extra term is the one I want to squash down.
Yeah, because I was wondering, like, if from the thermodynamic point, for thermodynamics, or non-Markovianity was like useful.
Actually, this is a very good point. So we had a discussion recently with Francesco Buscemi, and he was just saying, and I think this is something we're probably working on, but I should, yeah, thanks for reminding me, I should email him. Not all non-Markovianity is useful enough. So sometimes you can be in a room full of people and then you hear lots of noise, yeah, something like this. Maybe you have worked on this stuff, I don't know. There was a paper by Francesco exactly like this. So some non-Markovianity seems to be not useful, and indeed we wanted to isolate the useful one. And this might provide a lot more quality enhancement, because a lot in here is there, but doesn't really make a difference. But it's a very good point. If you have ideas, we can discuss more. Yeah.
Thank you.
More questions? Yeah, I have a. Oh, sorry. No, like looking for let's say to a bigger picture. The non-Markovian channel usually costs some work to prepare. Like, so you need to pay some energy price to create this memory, which
Yes.
appears in. I mean, it's like something that appeared, I think, in Max on Demo, something like that. When you take it into account, can you still find some, let's say, improvement on the work extraction?
Yeah, so this is something which I mentioned at this point, yeah, because our best protocol, it implies that we create some comb which is non-Markovian from our point of view. So we have to spend some energy to create it, which is this one. And then overall, combined with the process itself that we cannot touch, this will net more work than the previous step. So we have to make an investment here to create this comb, and this gives us some advantage, because we can, even if it costs more, then you get a lot better gain. It's a high risk, high reward, let's say. But what we don't have is the final form of this. So I think we can even lower this energy cost for creating the comb in some more clever way, and this will give us even more work. So we are open to ordering down this term from our point of view. That's an open question we left in the paper.
Okay. The other question is whether it's possible or not, or feasible to try to extend it to some continuous time dynamics.
I really would like to. I don't know. The whole structure, this one is very specific to the process tensor thing, but I was never happy with it, just because it seems artificial. So I think it's possible. I mean, there are some maps already, because of course this process tensors maps into tensor networks, and these things have been considered also in continuous case. But there are works related to this from Roberta, from Sabrina Maniscalco, and so on, related to specific dynamics for which, and I think you were involved as well, dynamics for which non-Markovianity plays a role for various thermodynamic processes. I would like to have a general, like universal approach similar to this one for continuous time. I don't know if you have ideas, it would be good to discuss.
Okay, thank you. Very nice talk.
Thank you. Thanks for all the questions.
Any other question?
But if not, let's thank Gerard again.
Thank you. Yeah, who works on SLD, Fisher information? Oh, because this is quantum metrology stuff. Very nice. It's a definition of quantum Fisher information. in critical systems.
No. This is correct. No,
It's SLD, yeah, it's the variance for pure states, no, the quantum fish.